I am going to take the seminar topic, that is overview of DC machines. I am T Dhanesh Raj, Assistant Professor in the Department of Biomedical Engineering. First, the topic is classification of DC machines. Here the DC machine is classified into two types. One is DC generator, another one is DC motor. DC generator is a electrical machine which converts mechanical energy into electrical energy. Otherwise, here the DC motor is an electrical machine which converts electrical energy into mechanical energy. Here the construction part is similar for the both machine, but the working principle is different. Here the working principle of DC generator. DC generator works under the principle of Faraday's law of electromagnetic induction. Here Faraday's law of electromagnetic induction means whenever conductor cuts magnetic flux, an induced EMF produced in it. Whenever conductor cuts magnetic flux, an induced EMF produced in it. That induced EMF causes current to flow if the conductor circuit is closed circuit. If the conductor circuit is open circuit, means there is no current flow through the coil. This is the working principle used in DC generator. Here you consider two magnets, that is two permanent magnets, north and south pole, that will attract each other due to the presence of magnetic lines of force passing from north pole to south pole. If you place a conductor material, means there is no effect. If you move the conductor material or rotate the conductor material, means that will cut the conductor produces an induced EMF. Therefore, here we are giving the input energy as mechanical energy, rotating the conductor, that is mechanical energy, that is converted to electrical energy. Therefore, this is the working principle used in DC generator. Similarly, in DC motor, the same circuit diagram. Here in DC generator, whenever conductor cuts magnetic flux and induced EMF produced it. In DC motor, when a current carrying conductor is placed between the magnetic field, it will experience a mechanical force whose direction is given by F equal to the formula B into I into L. B be the magnetic flux density, I be the current flowing through the conductor, L be the length of the conductor. That is the working principle used in DC motor. Here the current carrying conductor means that we are giving input energy is electrical energy, that is converted to mechanical energy. That is the DC motor working principle. Electrical energy, in that some supply voltage is there, that opposes the induced EMF. In DC motor, the generated EMF is otherwise known as back EMF. Next, EMF equation of a DC generator. The EMF equation of both the DC machine is same when working as a DC motor or generator. The EMF equation of a DC generator EG is equal to, the formula is pi Z and P by 60A. Pi is the magnetic flux, P is the number of poles, Z be the number of conductors, then N be the speed in RPM. This is the EMF equation for DC generator. Similarly, the same expression will be for DC motor. DC motor, that the generated EMF or back EMF, that is equal to pi Z and P by 60A. Here this in DC motor, the generated EMF is otherwise known as back EMF, because here in DC motor the working principle is electrical energy is converted to mechanical energy. In that electrical energy, supply voltage is there. Here the generated EMF that opposes the supply voltage. Therefore, that induced EMF is known as back EMF. In DC motor, the generated EMF is always known as back EMF. Next, we discuss about the types of DC generator. The DC generator can be classified according to the method of excitation. Here the method of excitation means the way of exciting the field current. Field current means the way of exciting the field winding. The current, by giving direct current flowing through the field winding, that produces magnetic flux. This is a method of excitation. According to the method of excitation, the DC generator is classified into the two types, that is separately excited DC generator, self-excited DC generator. This is a circuit diagram for separately excited DC generator. Here here separately excited means the field winding, this one is field winding, this one is armature winding. The field winding is excited from an external source of DC supply. Separate source of DC supply, we are exciting the field winding. This is known as separately excited DC generator. There is no electrical connection between this field winding and armature winding. Here this load is connected to across the armature winding, therefore same current flows through this circuit. Here this armature current, that's IA is equal to IL. By applying Kirchhoff's voltage law, we can get the voltage equation of the DC generator. Kirchhoff's voltage law means Kirchhoff's voltage law states that the sum of voltage rises is equal to sum of voltage drop in a closed circuit. Therefore, by applying Kirchhoff's voltage law, we can get the voltage equation of a separately excited DC generator. Therefore, that formula is EG equal to Vt plus Ia into Ra. In self-excited DC generator, there are three classifications. The first one is series generator, the second one is shunt generator, the third one is compound generator. Depending upon the connection of field winding and the armature winding, the self-excited DC generators are classified. The first one is series generator. Here this field winding that is connected in series with the armature winding, that is known as DC series generator. Here this field winding has less number of turns of thick wire, having low resistance property. Therefore, this circuit is series circuit. For series circuit, current should be same. Therefore, the armature current, the current flowing through the armature, that is IA, the current flowing through the field winding, that is ISC, then current flowing through the load. The three currents are equal. Here I suffix A equal to ISC equal to IL. By applying Kirchhoff's voltage law, we can get this generated EMF equation EG equal to, so V means voltage across the load, V plus IA into RA plus RAC. This drop can be neglected, that is the voltage drop across bus is very small, that can be neglected. This is about the DC series generator. Then DC shunt generator. Here this field winding is connected in parallel with the armature winding. This is known as DC shunt generator. Here this shunt field winding, this field winding is connected in parallel for shunt field winding, having more number of turns of thin wire, having high resistance property. Here this circuit is divided, so the armature current is divided into two parts. One part is flowing through the field winding, other part is flowing through the load current. Load. Okay. Therefore, this armature current IA is equal to ISH plus IL. Here the armature current equation IA is equal to IL plus ISH we can get by applying Kirchhoff's current law at this node. By applying Kirchhoff's voltage law, we can get this equation EG equal to V plus IA into RA. This is about DC shunt generator. Then DC compound generator, it consists of two windings, two field windings and armature winding. One is series field winding, another is shunt field winding. Here this depending upon the connection of shunt and series field winding, there are two types: long shunt compound generator and short shunt compound generator. This is the circuit diagram for long shunt compound generator. Here this shunt field winding is connected parallel with both armature winding and series field winding. This type of generator is known as long shunt compound generator. Here also the circuit is divided, therefore this armature current IA is divided into two parts, that is ISH and IL. Here IA is equal to ISH plus IL. Next one is short shunt compound generator. Here the shunt field winding that is connected in parallel with armature winding, and this combination is connected in series with the series field winding. This is known as short shunt compound generator. Here also this armature current is divided into two parts, that is IA is equal to ISC plus ISH. Next one is characteristics of a DC generator. Here the two characteristics, that is no load characteristics are open circuit characteristics, or another name is magnetization characteristics. The second one is load test characteristics. Here this load test characteristics, it is classified into two types, that is internal characteristics and external characteristics. This one is the circuit diagram for open circuit characteristics of a self-excited DC shunt generator. Self-excited DC shunt generator means here the field winding is connected parallel with the armature winding. Here the field winding is connected parallel with the armature winding. So this is circuit diagram represents the no load characteristics of a self-excited DC shunt generator. Here, no load characteristics means the graph is plotted between induced EMF at no load against field current. The curve is drawn between various values of induced EMF against field current is known as open circuit characteristics. Here in this circuit diagram, we are inserting one resistance, variable resistance that is connected in series with the field winding. By varying this resistance, we can get various values of this field current and induced EMF at no load. Therefore, the graph is plotted between induced EMF at no load against field current is known as open circuit characteristics. This is the open circuit characteristics of a self-excited DC shunt generator at different speeds, that is N1 and N2 and N3. So the curve is drawn between induced EMF at no load against field current. The curve increases linearly. This is the open circuit characteristics of a self-excited DC shunt generator. This next one is load test characteristics. Here this load test characteristics is classified into two types, that is internal characteristics, another is external characteristics. Internal characteristics means here the graph is drawn between induced EMF versus armature current, that is known as internal characteristics. Here the external characteristics means the graph is drawn between terminal voltage versus load current, that is external characteristics. Here the above one characteristics internal characteristics, the below one is external characteristics, because here this induced EMF is greater than the terminal voltage. Here the external characteristics means the graph is drawn between terminal voltage against load current. Therefore, the induced EMF is greater than terminal voltage. Therefore, the above one characteristics is external characteristics. Here load test characteristics means the output of the generator is connected to the load. Therefore, by applying various loads, we can note the various voltmeter, the ammeter readings. For that, we have to draw the internal and external characteristics. These are some applications of DC generator. So the DC generator means for laboratory and testing purposes, we are using the wide range of output voltages we can apply by using this application of DC generator. Then lighting and power supply and regenerative braking DC locomotives. Then we used to say voltage boosters, then providing exercises to alternators. These are the some applications for DC generators. Then I conclude my seminar.